The Spectrum Analyzer by Ian Eskandari and Matthew Hampsey. Ian was really looking forward to the Sydney Vivid Festival this year. Unfortunately, as an engineering student, he does not have any free time because he is always too busy doing assignments. Needless to say, this saddened him deeply. However, in the dark confines of the electrical building, an idea was proposed. If Ian could not go to Vivid, Vivid would come to Ian. The objectives of this project were to design a spectrum analyzer using an Arduino Due and an LED matrix to graphically display information about the frequency of an audio input, which is typically music. If time permits, the project will be extended to incorporate a wireless on-off button so that Ian doesn't have to leave his study desk. A further extension will be to implement a voice lock by comparing an input voice signal to a pre-recorded signal. Another possible extension is to sample the input using an external 16-bit ADC rather than the onboard ADC, which will improve precision. The initial design of this project consists of an audio signal source, either from a laptop, phone, or MP3 player headphone jack. This is input into the Arduino's analog input. Here, the onboard ADC is called via an interrupt tied to the system clock, which converts the analog signal into an array of values. Once this array is collected, a fast Fourier transform algorithm is called on the data, converting it into an array of frequency magnitudes. We will then use these frequency magnitudes to light up each of the columns of an LED matrix. The magnitude of each bin of the Fourier transform corresponds to the number of columns that it will light up, i.e., a larger magnitude will result in more LEDs being lit up. In this way, it will visually display information about the frequency spectrum. A number of problems were encountered with this initial design. Firstly, the chosen LED matrix was very optimized for the Arduino Uno, but not the Due. And there were timing incompatibilities because of this. These were improved by modifying some of the pulse width modulation timing in the library, but the flickering could not be removed completely. Additionally, this matrix was accidentally destroyed by a short in its adapter connection, which caused an input voltage of 12 volts rather than 5 volts, damaging the circuitry. This may or may have not been Matthew's fault. Unfortunately, this happened less than a week before the due date, so a replacement matrix could not be ordered. Instead, a red LED matrix was purchased from JCar. Thirdly, the electret microphone was damaged by a faulty capacitor, rendering it useless. Because of this, the voice lock extension was unable to be completed. When programming the matrix, it was found that it offered poor frequency resolution when music was played through it. This was because while human ears can hear from 20 Hz to 20 kHz, we cannot distinguish evenly between the whole range of frequencies. We actually have a lot higher resolution between 200 Hz and 2 kHz, which is the range that most music occupies. To fix this, we increased the number of samples and then averaged them out over a non-linear range of frequencies, approximately logarithmic. It was a greater resolution in the 200 Hz to 2 kHz range after this, which improved results markedly. Finally, we ran out of time and were unable to incorporate the external ADC. Instead, we had to use the onboard ADC. Our final design consisted of an audio output into the Arduino analog input. This was sampled and processed in the manner described earlier, and the output was used to control an LED matrix. An additional level of control of the matrix was provided by a Bluetooth module, which allowed the matrix to be turned on and off from an Android phone. And now for our feature presentation.
As you can see, we simply take the audio output from the headphone jack of the laptop and input that directly into the analog input of the Arduino. The Bluetooth module here is simply allowing communication with the phone to turn on the LED matrix. Output from the digital pins of the Arduino goes into the matrix, which then displays the frequency information of the audio signal. I'll turn down the light so we can take a better look.
If you also bring your attention to the phone, we can see that by pushing F, we turn the matrix off, and by pushing T, we turn it back on, demonstrating the Bluetooth module wireless capability. This concludes our presentation. Thank you very much for your attention.